In today's lecture, we will be considering X-ray, its history and production. Everyone on the planet is exposed to a certain amount of radiation as they go about their daily lives. Radioactive material is found naturally in the air, soil, water, rocks, and vegetation. The greatest source of natural radiation for most people is radium. The Earth is constantly bombarded by cosmic radiation, which includes X-rays. These rays are not harmless, but they are unavoidable, and the radiation is at such low levels that its effects are virtually unnoticed. Pilots, cabin crew, and astronauts are at more risk of higher doses because of the increased exposure to cosmic rays at altitude. X-rays are a form of high-energy short-wavelength electromagnetic radiation, 0.01 to 10 nanometers, that act as an essential non-destructive probe for studying the atomic and molecular structure of matter. Discovered in 1895 by Wilhelm Röntgen, they have since become foundational in both physics and chemistry, primary for investigating crystalline structures, analyzing elemental composition through diffraction, and spectroscopic techniques. X-rays are high-energy electromagnetic waves with tremendous penetrating power. By packing energies between 100 electrovolts and 100 kiloelectrovolts, they pass through materials opaque to visible light and interact with atoms to create everything from medical images to deep space astrophysics data. The penetrating power of an X-ray is determined by its wavelength. Because X-rays have incredibly short wavelengths of 0.01 to 10 nanometers, they can pass directly through solid objects, including soft human tissues. When passing through the body, less dense tissues like fat allow X-rays to pass through easily, while denser material like bones absorb them. This absorption difference is what creates the contrast on an image. X-rays are powerful enough to strip electrons away from atoms and break chemical bonds, a process known as ionization. Because this ionization can damage DNA, medical professionals carefully control the dosage. The overarching rule in radiology is to use the lowest possible dose that still yields an adequate diagnostic image. Wilhelm Röntgen, a German professor of physics in Würzburg, Bavaria, discovered X-rays in 1895 accidentally while testing whether cathode rays could pass through glass. His cathode tube was covered in heavy black paper, so he was surprised when an incandescent green light nevertheless escaped and projected onto a nearby fluorescent screen. Through experimentation, he found that the mysterious light would pass through most substances but leave shadows of solid objects. Because he did not know what the rays were, he called them X, meaning unknown rays. He won the first Nobel Prize in Physics in 1901 for his work on X-rays. Wilhelm Röntgen discovered their medical use when he made a picture of his wife's hand on a photographic plate placed due to X-rays. The photograph of his wife's hand was the first photograph of a human body part using X-rays. When she saw the picture, she said, "I have seen my death." Taking an X-ray image with early Crookes tube apparatus in the late 80s, as shown in Figure 2, the Crookes tube is visible in center. The standing man was viewing his hand with a fluoroscope screen. The seated man was taking a radiograph of his hand by placing it on a photographic plate. No precaution against radiation exposure was taken, as its hazards were not known at that time. The early use of X-rays was widespread and unrestrained, even to the degree that during the 1930s and 1940s, shoe stores offered free X-rays so that customers could see the bones in their feet. Though there were a few early suspicions from scientists including Thomas Edison, Nikola Tesla, William Morton, each of whom reported injuries they believe resulted from experiments with X-rays. Thomas Edison started research soon after Röntgen's discovery and investigated materials' ability to fluoresce when exposed to X-rays, finding that carbon tungsten was the most effective substance at that time. In May 1896, he developed the first mass-produced live imaging device, his Vitascope, later called the fluoroscope, which became the standard for medical X-ray examinations. Edison dropped X-ray research around 1903 before the death of Clarence Madison Darley, one of his glassblowers. Darley had a habit of testing X-ray tubes on his own hands, developing a cancer in them so tenacious that both arms were amputated in a futile attempt to save his life. In 1904, he became the first known death attributed to X-ray exposure. Darley is thought to be the first American to die from the effects of experimentation with radiation. Following this, Thomas Edison abandoned his research on X-rays. He said, "Don't talk to me about X-rays. I am afraid of them," in 1903. The figure 3 here shows the schematic description of an X-ray machine. You can see the lead casing. We see the glass containing vacuum. We have the cathode, we have the focusing cup, we have the filament, the window, the X-ray beam, the target, the anode, and then the oil for heat conduction. I will quickly explain each of these to our understanding. The lead casing on an X-ray machine is basically a radiation shield. It matters because X-rays are ionizing radiation. They can damage cells and DNA if one is exposed too much to it. The glass envelope contains vacuum, does three things. It lets electrons travel without colliding. Inside the tube, electrons are boiled off the cathode and accelerated at high speed towards the anode to produce X-rays. Air molecules will get in the way and scatter those electrons. So the vacuum removes air so electrons can fly straight from cathode to anode without losing energy or direction. It prevents the filament from burning out, and it insulates and contains the higher voltage required for X-ray. We have the cathode. The cathode is the electron source. It produces and controls the electron beam that slams into the anode. It emits the electron via thermonic emission because of enough heat. It contains the tungsten filament. It focuses the electron beam with the aid of the focusing cup, which shapes the cloud of electrons into a narrow beam and aims it at a small spot on the anode. It also controls X-ray quantity through the amount of current passed. What is the work of the filament? The filament is usually a small coil of tungsten wire built into the cathode. Tungsten is used because of its high melting point, low vapor pressure, and high atomic number. It can get hot enough to emit electrons without melting or evaporating. We also have the target. The target is the part of the anode that the electron beam actually hits. It converts electron energy into X-rays. It handles extreme heat. It is angled for beam direction. There are two types of target, the stationary and the rotating target. The stationary target, the beam hits one spot used in low power tubes. The rotating targets are used in diagnostic tubes. It is a spinning disc, so the beam hits a new spot each millisecond. This spreads the heat over a larger area and prevents melting. The X-ray windows, as shown here, allows the useful X-ray beam to exit. It is made up of low absorption material, usually beryllium or thin aluminum. What of the anode? The anode produces the X-rays. The anode loses electrons through Bremsstrahlung. Electrons get slowed and deflected by tungsten atoms, releasing energy as X-rays photons. The anode produces characteristic X-rays of specific energy. The anode dissipates heat. Only about 1% become X-rays, and the other 99% will be heat. The anode is the positive electrode. We have the oil for heat conduction there. The oil absorbs and transfers the heat as the anode releases 99% of electrons as heat. The oil insulates the high voltage. The oil dissipates heat to the housing. The hot oil rises while the cooler oil sinks, creating a natural flow that moves heat away from the two. The oil also dampens mechanical shock. The X-ray production itself. High voltage transformers are used up to 40 to 150 kilovoltage peak to accelerate electrons in the cathode, which has a negatively charged filament. Imagine a vacuum tube with two electrodes on opposite sides, vacuum housing that contains the cathode and anode. No gas or air is allowed inside. On the cathode side, there is a filament that gets heated by passing a given current. The filaments are heated to convert the electrical energy to heat energy. When heated, it boils off electrons, which is called thermionic emission, the process of producing electrons through heat. The heat produces a cloud of electrons that hangs around the cathode filament. The emitted electrons are accelerated towards the positively charged tungsten target because the cathode is negative, unlike terms attract. Electrons smash into it, and approximately 0.05 to 1% of the kinetic energy of the electron becomes X-rays. That 99% becomes heat. Properties of X-rays. X-rays are high energy ionizing electromagnetic radiation with very short wavelengths, 0.01 to 10 nanometers. They are invisible, massless, and neutral, no charge, traveling in straight lines at the speed of light, and are not deflected by electric or magnetic fields. They have high penetration power. They can fluoresce in certain substances like zinc sulfide or calcium tungstate, can cause biological damage to tissues, and has the ability to produce images by ionizing matter. X-rays are part of the electromagnetic spectrum, possessing both wave and particle characteristics. Photons. X-rays can ionize air particles. X-rays has no momentum. X-rays affect photographic plates. Types of X-rays. We have X-ray crystallography. It's a powerful technique used to determine the 3D atomic and molecular structure of crystalline material by analyzing the diffraction patterns produced when X-rays pass through them. By measuring the scattering angles and intensity, researchers can calculate electron density maps to build atomic models. It is crucial for studying protein structures and pharmaceutical designs. We have radiography. This is the most familiar type of X-ray imaging. It is used to image broken bones, teeth, and the chest. Radiography also uses the smallest amounts of radiation. We have fluoroscopy. The radiologist or radiographer can watch the X-ray of the patient moving in real time and take snapshots. This type of X-ray might be used to watch the activity of the gut after a burial meal. Fluoroscopy uses more X-ray radiation than a standard X-ray, but the amounts are still extremely small. We have another type called the computed tomography, CT. The patient lies on a table and enters a ring-shaped scanner. A fan-shaped beam of X-rays passes through the patient onto a number of detectors. The patient moves slowly into the machine so that a series of slices can be taken to build up a 3D image. This procedure uses the highest dose of X-rays because a larger number of images are taken in one sitting. We end the lesson here today, and in the next lecture, we will be looking at the applications of X-rays. But try to answer the following questions. Question 1. Give a brief history of X-rays. 2. List the components of an X-ray machine. 3. Give 6 characteristics of an X-ray. And 4. Explain the types of X-rays. If this lecture have interested you, don't fail to subscribe, like, and share this video with your loved ones.